Hi everybody, my name's Paul. I work at Google with Dan, and we work on LLVM for Fuchsia and supporting a lot of the embedded systems at Google. So today we're going to tell you some of our experiences trying to use LTO with libc as source. So to give you like a brief overview and get everybody on the same page, I'm going to talk about the full LTO pipeline. Unlike most projects at Google, we are focused very much on smaller projects where size is probably the largest concern, and full LTO still does much better in terms of size optimization than thin LTO. So to start out, the linker gets a set of LLVM IR, performs some kind of symbol resolution, and then passes control off to the LTO pipeline, which starts to merge the modules, performs internalization, and then you end up with sort of a monolithic chunk of LLVM IR that's pretty much the whole program. We run optimizations on it, do code generation, and then regular elf linking sort of resumes from that point, and then you end up with your final output. And sort of to motivate like why we want to do this in the first place, we are big believers in the power of the compiler and maximizing its opportunities to do the good things that it already does. In a lot of ways, LTO is about maximizing those opportunities in the first place, right? Like we're merging modules together to sort of blur the boundaries that the compiler that we introduced by having separate translation units. And so we want to have the compiler, to give the compiler the opportunity to optimize interfaces, to remove as much code as it can, and really that's like our main incentive is to maximize these opportunities. So what happens if you actually try this? You fire up Clang, you pass FLLTO to it, you pass it, your libc compiles as bitcode, and lo and behold, it blows up in your face. Here I have a undefined hidden symbol for bcomp, and that's pretty weird because bcomp is part of the source I compiled. It's in my .a, so let's see what's going on. I'm, an experienced compiler engineer. I know about save temps. Let's do that and take a look at what's going on in the optimization pipeline. So you might notice that I have the definition of bcomp. And, this kind of doesn't really make sense. Like, why am I having a problem with this undefined symbol when it is in fact here? So let's dig into this a little bit. So here's a simplified example that we're going to use as sort of a running theme for the stock. I have some function foo. It has a call to memcopy. It's using that in a branch, and then it's going to return some value. It's not really important what it's doing. So I have memcomp here. It's available as an external symbol, and I have bcomp. And so after global DCE runs, bcomp is not referenced, and the compiler does what's generally a very good thing. It deletes it. It's dead code, nobody's calling it, so it gets rid of it. And that seems fine. Right now the code is good. But a little bit later, ins-combine runs. And part of ins-combine is to run simplify libcall. And what this has done is it's changed the call from memcomp to bcomp, because I was using this as the condition in a branch, or effectively the same way. And I don't know if you noticed, but like bcomp is also back in my module as a definition and not just a declaration and not a definition. It's just some external reference that I now have. And so when the link finishes, everything blows up in my face. And this was sort of my table flip moment. Like, I just could not fathom how this was possible. So to summarize what happened, all the libc APIs get marked as internal because this is just part of LTO's normal start. Global DCE comes along, sees bcomp isn't used and deletes it. Simplified libcall does me a big solid and optimizes it by reintroducing this call to bcomp, and linking breaks because bcomp is no longer around. And this is the point where like I'm very sad. So what's actually different about using LTO with libc? Clang has sort of a large set of assumptions, and most compilers in general, about what libc is and how it can be used and what these interfaces are sort of based on. Clang assumes things about libc based on whether on the model that you're doing static or dynamic linking, and these interfaces are guaranteed to be sort of provided, right? It's an abstract interface from the point of view of the compiler. And this is good because we want to be able to do high-level transformations, to do things like pattern match against memcopy, to do this exact optimization that's sort of blown up in my face, like changing memcomp to bcomp. And the way you control this when you're normally building your libc and other stuff is through things like fno built-ins. The compiler also has sort of a set of low-level transforms for things like libcalls and built-ins that happen in the back end. And there's no way to opt out of those. Those are sort of just like part of like how the compiler is always going to work. And those are handled specially. So these runtime libcalls seem pretty attractive. And this is sort of like, how memcopy sort of, handles this situation. So the first thing we thought of was like, all right, well, we'll just try that. Because these are treated differently by the optimization pipeline. And they can't be removed because they're expected to provide a definition potentially externally, right? They're also always extracted from like a bitcode archive, so it's going to be around for all the things to use, which is great. And so, like, why not actually just use this mechanism to get the compiler to work the way that we want? So before I get to that, I made this patch, and Eli Friedman very, helpfully explained to me why this was a problem. A lot of the previous slide is actually direct information from him about how the compiler treats these features. And so what he sort of proposed was that we actually have a sort of conceptual split between a world where built-ins are allowed to be used, things like memcopy and bcomp and these libfunc, these things we define as libfuncs, and this is just the period of time where you can treat libc as a completely abstract interface, right? And the way LLVM uses this mechanism more generally is through no built-ins, right? And so conceptually, we want to partition the compiler pipeline into two halves. One where it's just an abstract interface that the compiler can always use, and another one where you enter a no built-ins world, and you just have a soup of IR, and the optimizer just treats it sort of as one big thing that it can just do whatever it thinks is best. And so this is sort of what we started sketching out. And so if you're thinking about how you would encode this in IR, sort of the most naive thing to do is to say all right, well, I can just slap the no built-ins attribute on all the functions in the module and pick some place in the pipeline where this is going to be safe, and let's see what happens. And so I built this pass, and it's a very naive pass. It literally just does what I said. It just puts the attribute on everything, and the compiler continues along. And lo and behold, this works. Bcomp can't be DCE because it's illegal to rewrite memcomp to bcomp because it's not available, and this never gets replaced during global optimization. Unfortunately, it really works because what I've done is actually slightly a lot, right? When I slap no built-ins on this, I actually changed a considerable amount of the compiler's behavior. Putting no built-ins on all of these functions, no matter where you put it in the pipeline, is going to affect a lot of what goodness you would ever get out of TLI in the backend. And so something like this, where you'd want to replace this call to square root finite, and you normally get a single instruction on x86 replacing it, can no longer happen. And this is sort of throwing the baby out with the bathwater, right? And I'm going to hand the rest of the talk over to Dan, who's going to talk about how we're actually going to build a more proper built-in.
Yeah, so, okay, I was kind of in discussions with Paul on a lot of this stuff, that kind of taking a back seat. And kind of the reason I was interested in this is because in my goofy side projects, similarly, we had just decided, oh, we'll LTO all of the things. We're on a tiny embedded system, what could go wrong? And for us, nothing actually went wrong, which was very surprising, given all of the stuff that we just talked about. a lot ostensibly is wrong. And one of the things that kind of led into what I'm about to talk about, like having this kind of more sanitized notion of built-ins and how we treat them, especially post-link, was that like it's almost right today. Like you could think of a world in which built-ins exist and operate normally as being everything that happens before you link IR together. But then once you link IR together, then you can't necessarily do arbitrary transformations. And Paul's patch, which he had tried, was like the simplest place to have this cut between I know what built-ins are and what they do, and I don't know anything about them, would be like at the link line. Like once you've decided what you're bringing into the link and what you're not, then you can just disclaim all knowledge. But of course, we discovered that turns off like a ton of things because you do actually want to know what functions do post-link. Like that's when you're generating code in LTO that you really, really need to know things. So it wasn't quite as simple as just making the cut the link, as much as that would be conceptually nice. We needed to find a way to have stuff after the link have a more refined notion of what you can do with these symbols. So we spent some time thinking about it, and some of this came from Eli, some of this was just back of the envelope stuff between me and Paul. What we came up with is a set of rules for how to safely use functions after the link is finished. So first rule, if something made it in to your link and is in bitcode, it's probably safe to add references to it. Like, in this case, we had bcomp get pulled in for one reason or another. This memcomp can be turned into a call to bcomp because we made it in. Like, it's in our link. It'd be kind of silly to not allow transforms like this to happen. And so we want a world in which we can allow some of these transforms that are safe to happen. But for this to be safe, sorry, I had this check mark. For this to be safe, we really need to know that if we do one of these transforms, and we're going to allow ourselves to do these transforms absolutely at any time, then what we're transforming to has to be sacrosanct. It has to be treated as carefully and set apart in such a way as if it was basically something that you pulled in. And thankfully, LLVM already has kind of a mechanism for this. You mark it as used externally. You pretend that there's something out there in some code that you can't see that calls this as is, and thus you're not allowed to futz with it. You're not allowed to delete it. You're not allowed to delete arguments from it. You're not allowed to change its API in any way. And actually just setting its linkage type to external and not letting it be internalized does that. So if you do that, then this thing gets marked as not being able to be futzed with. And this case that we had where you have it going away during DCE, that actually just can't happen. So that actually takes care of about half of it. The other thing that you can't do, which is something that wasn't in this example, but we've also been able to make examples that broke in similar ways, is you can't allow people to allow passes, the compiler's not people, allow passes to add references to things that didn't make it into the link. Like, because you have finished linking, the set of libc functions that made it in and didn't make it in, that's frozen. Like, it's not going to be reasonable to halfway through the compilation process decide that you have some extra bit code that you want to run through all of the stuff that you did, including inlining and things that are that way lies madness. So you do the link, the stuff that made it in, the stuff that didn't make it in. And so in this case, for this example, if bcomp ended up actually needed for anything, it's kind of not reasonable if you notice some code pattern after the link, rather than before the link, that now because of inliner or whatever, you can discover that you can turn from memcomp to bcomp. Well, I'm sorry, that's too bad. You didn't know that you needed bcomp. The link is already over. Like, we consider it a reasonable trade-off to disable cases like this, where you're going to insert new references to functions that are outside the link. So we actually built a patch for this to do this, and much to our surprise, it actually wasn't terrible. It's like a couple hundred lines at this point. It's pretty reasonable. It touches a lot, but the ways in which it touches everything are pretty small. So I'll kind of go through a little example of how what we built works, and then we can talk about the details of this, and all of the stuff that is around this that we kind of want to move forward with upstream. So this is like a little brief summary of how it works, but I'll go in specific. So the very first thing that's going to need to happen to have a model of this is LLD needs to get knowledge about what are these functions. And it needs to do this because it's going to have to collect information about whether or not these things are in bitcode later. So We actually do have prior art for this in LLD. There's a little function that is called get runtime libcalls, because similarly, the runtime libcalls are treated specially by the link, and they need to summarily be brought in. And so this was something that really annoyed me. I used to call it the list. Thankfully, someone killed the list, and now it's an actual function call with good semantics. But there used to actually just be a static list that was table gen of absolutely every string that was a runtime libcall. And it didn't actually have all of them in it. So, because of course it didn't, and like if any of them was wrong and they were in bitcode, then they wouldn't get brought in. But like that actually has been fixed, and I'm very, very happy about that. Similarly, we can add a what are all of the C library functions call, and that, that's a bit of data, but that's not actually that bad. You can give a target triple to target library info, have it construct itself. All of that decision making is just based on the target triple, and you can get a conservative list of what are all of these functions, what could they be. And then in response to that, in this case I have memcomp, bcomp, printf, memcopy, all of the others. It's pretty easy in the linker to go through the symbol table, see what all of these symbols resolve to, which of them actually are available or not, and for the ones that are available, maybe some are some mismatch or whatever. Which of these actually are in bitcode? The ones that are in bitcode are the only ones that we might have some problem bringing in late. If things aren't in bitcode, then totally fine. So in this case, between these two, we can say that memcopy is a hand-coded assembly implementation. And if you have an actual object file that backs one of these, then, well, there's nothing more you need to do with this. So one of the nice properties that this gives this approach is that it's a complete no-op unless you're actually trying to LTO in your libc. Which is one of those things that might have us have a prayer of actually like having this be upstreamable. So the only actual overhead for full LTO would be that you would query LTO and construct an array with a bunch of strings in it, which is it's a thing, but it's not that big of a thing, and it's something that target library info already does a ton of times anyway. So once you have that list though, you can go and ask now. All right, we've got these libcalls. We know that all of them are in bitcode. And we can actually scan through in the LTO side all of the IR that we received in full LTO, and in thin LTO, we can go through the module summaries and we can ask, okay, which of these made it in? What is our set of allowable libc calls? Like, what is the libc that made it into our project by direct call, by something being needed? And then we can freeze that list. In this example, I have memcomp and bcomp. They made it in. Printf didn't make it in. And finally, the LTO process that is going to invoke code generation and optimization, when it itself is the thing that's responsible for constructing this target library info object that says what parts of libc are available. And during that construction, you can actually go through, take this list of things, and for anything that has, didn't make it into the link, the things that are crossed out in that previous slide, you can disable them so that they're not allowed to be called. And then the ones that did make it in, the ones that were on the previous list but not crossed out, you can say, okay, these are the ones we're allowed to call, so we're going to treat them as sacrosanct. We're going to mark them as external and not allow any optimization paths to touch their API or API. That does actually appear to work. It passes through the LTO test suite with only a couple breakages that have to do with the tests literally assuming that you can do this unsafe transform that we're trying to disable. So we have a modicum of confidence that this is kind of an okay thing to do. There's probably going to be a lot of quibbling about the spelling of all of this. Like I just lazily monkey patched things into interfaces in a way that could almost certainly be way more elegant. But we think that this is kind of a way that this problem could be solved it's like among the first principled approaches that we've had for this. And like we mentioned, this built-ins world that we have where we know what the built-ins are is something that we might be able to exit and at some point in the late pipeline allow you to discharge this I'm going to keep them as external and sacrosanct notion and start allowing you to do optimizations on them. Like if we can find a point late enough that we're not going to do renamings of symbols and we're just going to futz with IR directly, then we might be able to find a cut and get a little bit more good out of our optimization pipeline. So, I think that's kind of the approach we have. I'll pass it over to Paul for the rest.
So briefly, where are we going to go from here? We still have some more evaluation to do. I was really hoping to get something more broadly, tested across Google. I don't think using the static libc at Google scale is quite ready yet. But we have several embedded projects that we're investigating with right now. It seems to be working well. They're getting some pretty good code size improvements. We think there's still some tweaking we can do to make it work even better. There's going to be a lot more discussion with our upstream partners. Everybody in this community is who we're talking about. We want your help. We want your advice. I wouldn't have got here without Eli's advice or the advice of lots of other people. Like, I've been talking about this for a while. There's other questions like, do we need new attributes for libc that would make this work even better? Do we want to make changes to the pass pipeline? Is encoding some of this stuff in the IR in a more like principled way, the way that we want to go? In the future, do we want to also consider doing things like this for built-ins? Maybe, maybe not, but this is all about unlocking the potential of the compiler and letting it make the decision of whether this is a good idea or not. It should work, probably in practice, but whether we want to or not is sort of an orthogonal choice. And I think the other thing that we actually want to hammer out is, what are the exact semantics of LTO in all these cases? How does it differ from a traditional linking model? Is that different between the different object file formats? Are we compliant? Are we doing something strange? Are we being consistent and principled? This is a big community. We don't think we'll get there alone. Whatever other people in the community are thinking about are probably things we want to discuss and help move forward. And with that, let's open the floor for questions. We have an old-ish RFC that discusses some of these issues with ELF. Feel free to chime in there. We'll be posting updates and links to our patch in the coming days.
Bravo, guys. Thanks for taking cracks at this. Super interesting stuff. I feel like, the initial problem you described is like a phase ordering hazard, essentially between global dead code elimination and libcall simplify, just assuming that these functions are always there, always available. And, I think issues that I personally have with libcall simplify is like, what version of libc are we talking about? They add more functions each C standard, and I don't think libcall simplify does a great job of saying the user intends to target C99 versus C11 versus C23.
Well,
and
it's not a language property, it's a system property.
And I think the same thing applies to compiler RT, and like, what versions of these things are you using? And especially LLVM libc being highly configurable. You could do a build of LLVM libc that's literally just memcopy and nothing else in it, right? If you wanted to.
So
I guess
our embedded targets are using LLVM libc, so we're able to leverage that a lot. I'm looking forward to finding new opportunities there. So yeah.
I guess questions I had, does your marking of the libc functions as external linkage fully pessimize dead code elimination for libc provided symbols that are truly dead?
I think in part we're relying on linker GC, but I think if they're really dead at the end, there's something that runs quite late that will get rid of them.
So one of the things that this buys us is we actually do get a little bit closer to the, I guess it's the case that if you have TUs that have if you have the traditional libc model with one TU per entry point, then there actually has to be a reason that one of these was brought in. And the only case that you could end up with something dead, because there will be a real call, is if inst simplify change that from a call that did make it in to a different call that made it in. But admittedly, so a bit niche, but that still could happen. And you could end up with something that was brought in and used a whole bunch, actually ends up dead. I do think one of the things that we could do, and I'd like to do, is to run a late global DCE pass. One of the things we talked about is
you split the DCE pass into two.
Oh yeah, or just another instance of it, essentially. If you are willing to say, okay, past this point, it is a pass ordering problem. If you're willing to say, past this point, we will not rewrite, we will basically disclaim any knowledge. And you can do that with TLI. You can just put no built-ins on every function, essentially, and disclaim any knowledge of what anything is. And if you do that, then it's safe to rewrite whatever, because you know that you're never going to manipulate the IR in such a way that a pass is going to depend on it. And we actually do a good job of making sure that when we need to know something about a function, we ask TLI whether we're allowed to know anything about that function. So I think it'd be just a matter of manipulating the pass pipeline a bit, and that's one of those things we wanted to talk to people about, is whether it's worth it to do this. Like, what are the trade-offs in performance for people to care about this and don't care about this? Like, how do we actually structure all that? We were just at the very beginning of even thinking about
I
it.
guess the other part that I was curious about, so, I recognize the issue you described with having the list, and the list getting stale as more library functions are added to the language, or your libc being configurable, or what version of compiler RT are we talking about, since target triple doesn't encode the versions of these things, right? Is there a way maybe someone can say, like, all of the symbols provided by this TU being brought in through LTO, like, this is the libc side channel, so we don't have to go and annotate every function in the libc or something?
This is some of the
Simple,
ideas
yeah.
this is what we're sort of talking about. Like, do we need annotations libc? Other things we should mark up? Do we need a new mechanism? I think this is going to be an ongoing discussion for a while. I think this gets us to maybe the first version where this is like not doing an explicitly like wrong thing and blowing up in your face, and it's not optimal. We're going to have a bunch of work to figure out all the ways to spell this in more sophisticated ways, unlock new optimizations, teach some of the optimization passes that there's more sophisticated, invasive things that they can maybe try when we mark them up the right way to say, like, hey, we're your partner, right? I think Matt has a question.
Okay, so I posted a patch to add the boilerplate for the runtime libcalls analysis. So I'm trying to get, like, I do not care about target library info at all. Like, that is not, the thing that I care about is runtime libcalls, because most of the calls synthesized by the compiler are there. And it's stupid that we have this split where they both do the same thing, but they're just like slightly different. I want to get everything in there and then be able to modify the set of, we can track both the versions and which functions are available in this analysis based on the link point. There's module.
That'd be amazing. Thank you. Like, I'm very happy to support that work, and you'd make our lives easier, I think. So thank you. Any more questions?
All right, we are out of time, so we give a warm round of applause for Paul and Daniel.